All right, let's get ready for the talk. I see some people still outside. Okay, let's get ready. So next talk, the last talk of today is by Professor Ioannis Papoutsis. Not sure if I could pronounce correctly. Ioannis is a professor of remote sensing and artificial intelligence at NTUA and an adjunct researcher at both the National Observatory of Athens and the Archimedes Research Center. He leads the Orion Lab Research Group, focusing on big satellite data analytics and machine learning for Earth observation, with emphasis on natural disaster management and climate change impact monitoring. It's my great pleasure to introducing him, and he will be giving talk entitled From Space to Safety with AI. Let's welcome him.
Thank you very much for the introduction. I'll start here, maybe I'll take this one as well. So thank you very much for the invitation, for being here in the introduction. I'm really excited to be here for the first time in Sofia. We're so close, but still it's the first time that I came here. So my talk would be kind of in the border between disaster management, foundation models, and uncertainty quantification. So I'll try to address these three different aspects. We all see this rapid rise of AI systems, large language models, that are already transforming the way that we work, the way that we collaborate, even the way that we communicate. And we also see that there are risks associated. So we have, this blurring of the boundaries between what is truth, what is misinformation, reminding us of all these risks and responsibilities that come with such powerful technologies. But at the very, at the same time, I want to argue that we have we can use the same methods to accelerate scientific discovery using machine learning and deep learning. And we can develop methods and technologies that can, let's say, save people's lives, make people's lives better in this complex environment that we are living, from forecasting disasters, assessing their impact in the light of climate change, and anticipate these impacts on the ecosystems as well. So this is what drives our research in the National Technical University of Athens, and this will be the focus of the presentation. I will start with a slide that I took from this very nice publication from Marcus Reichstein. Was published in Nature Communications, that is trying to address the following question: whether we can anticipate disasters accurately in time and across different landscapes and geographic contexts using Earth observation and AI models. And they are proposing this, how they call it, the 5 bridges of death, which is a nice title. So we go from measurements, observations. I can take the mic. Yes. We go from measurements to forecasts, weather forecasts, physical models that we know that are working very well. Then we move to forecasting hazards. So we are bringing other things into the equation, not just weather forecast. Impact forecast, so how the ecosystems, people, the economy will be directly affected. And moving to the communication of the disaster, of the early warning, and finally to what matters most, which is the decision-making process. And the argument here is that this chain is as strong as its weakest part. So, for example, we have very good weather models that are able to forecast with very good accuracy, at least at the short term. But this is not important if we cannot anticipate the hazard or the impact, because the very same, let's say, weather pattern can have a completely different effect when it comes to floods, for example, depending on the landscape. And similarly, when we go to communication science, what kind of information do we extract when we say, for example, that we expect 300 millimeters of rain? Should I be worried about that? What does this mean? So communicating this in an effective way is not a trivial thing. And again, from the same publication, what the authors propose is having this kind of model of what I see it as a mixture of experts. So you have different foundation models, one that is able to let's say, model the Earth system, the complex Earth system processes. One that is able, the Geospatial foundation model that's able to do this mapping, detection, and forecasting, and one that is able to communicate this information to decision makers and in order to make informed decisions. And this nice figure on the right, again from another publication from Gustavo Camvalls in Nature Communications, they try to decompose how we can use AI to support extreme events modeling. So we have these three pillars. The first one is about detection, forecasting, and impact assessment, always using machine learning and deep learning. Then the second pillar is about understanding and trustworthiness, so how we can trust these predictions and these forecasts. And these entails things like explainability, causality, so in a data-driven way identify these cause and effect relationships, and also be able to model counterfactuals and answer counterfactual type of questions, what-if type of questions, what would happen if there was an increase by 1 degree in the temperature, what would be the impact, so these kind of questions. And also estimate the uncertainty. So, because machine learning models are deterministic models in principle, so they are very confident for their decision, but the real world is not about confidence, it's all about uncertainty. So, uncertainty quantification is also very critical. And finally, we have this latter component that's about communicating all this information. And here we have this gap of how we go, how to say, call them the last mile from models to operational situations, operational decision-making, risk and ethics, and policy decision-making. So these are not, again, trivial things to address. And in this talk, I would try to address these three components, because I cannot go through all of them, of course. So how we at the lab try to do forecasting when it comes to disasters, how we estimate uncertainty, and what is the role of foundation models in this big picture. And when we are referring to the use of Earth observation and artificial intelligence for disaster management, there are some very specific challenges that I would like to address. First is that the fact that it's a big data problem, and big data is not just about volume, it's about the diversity, the multiple modalities observations that we have in place to observe physical phenomena and study disasters. We have a labeling problem, and I will come to that later on, meaning that by definition, extreme events or disasters are rare phenomena that do not happen every day. So it is, there is a big class imbalance when it comes to machine learning terms, and also the data generation process can be very noisy, so we have a noisy labels problem as well. As always, in most remote sensing applications, we always have the issue of, let's say, generalization, how we can generalize in different environmental conditions, landscape, agricultural practices, vegetation growth, let's say, signatures and spectral signatures, so generalization is critical for these applications. And as I mentioned, predicting is important, but estimating uncertainty and communicating what for which forecast we are not certain is also very important. And finally, I'd like to stress that these are very difficult problems when we're trying to forecast a natural disaster. It's very stochastic in nature, very complex. It implies many nonlinear, let's say, interactions happening under the hood. So modeling this, of course, with physical equations is very difficult, but with machine learning as well is quite challenging. So I will try to go directly to a specific application, which is about forecasting, let's say, wildfire danger in the short term. So in next day, next 2 days, next 3 days, like we do with weather forecasting. And this is a big data problem and mostly very stochastic in nature. And very stochastic because we have all these different variables that play a significant role in the onset and the spread of a wildfire. So we have variables that come from weather, from climate, so relative humidity, temperature, rainfall, all these well-known parameters, but also we have parameters that come from the vegetation status that are proxies to the flammability of the vegetation, so the fuel load, fuel characteristics, fuel moisture, and so on and so forth. And of course, we have the human, let's say, factor into the equation as well that plays a role in how we manage wildfires. So if this is I have this figure because this is just to highlight that this is a very complex problem to solve. And how we solve it as we typically do in machine learning. We collect all this data. So we have, we know very well for the past 20 years at least, where we had burnt areas, the time stamp of the burnt area. We know the conditions when we had the onset of a wildfire. We know the weather when we had the onset. We had the conditions of the vegetation from satellite data. We have all this information, road density, population density, which act as proxies of human activity. So we have all this information that when we try to visualize this, and I don't know if you can see it in this figure, but here in red we have the burnt pixels, so pixels that were actually had a wildfire. With blue are pixels where we didn't have a wildfire, and we plot the histograms depending as a function of many of these variables that we collect and harmonize in an Earth system data cube. And this is just to show that there is some information that can help us discriminate between what is going to burn and what is not going to burn. But if we see it as a unified system, as an Earth system is, then it's very difficult to create some heuristics to predict the wildfire danger or onset and spread. So before going to some results, just to mention some challenges when it comes to spatiotemporal modeling. So first of all, we have, when we collect all this data in an Earth system data, you have many things that are autocorrelated. So we have variables that are close in space that are correlated. For example, land surface temperature is one such variable. We have variables that are close in times that are correlated. For example, NDVI. We do not see many changes of big changes in the NDVI from one day to the next one. So these are things that we need to consider when we're splitting our data set so that autocorrelation is accounted for. The second is that it is nice that we have all these variables in an Earth system data cubes, really a lot of drivers, wildfire drivers, but it can be also a curse, and it's the curse of dimensionality, because we imply that we need all this information, all these different, let's say, dimensions to solve the problem. So the more dimensions, the more data that we need in order to avoid overfit in machine learning terms. So this is something to consider when we are building up the input, let's say, variables. And last but not least, we have to account about the Earth geometry, which the problem is that in different grid cells in these cubes have unequal area, and this implies also that distances between neighboring cells are not constant. And there are solutions to that. I have here a nice publication by Mark Rusum that they're trying to find clever ways to address this using these spherical harmonics. And I go directly to some results. So this is the ROC curve for predicting wildfires for the next day. The diagonal is the random classifier, and the better, the more we're on the upper left, the better is the prediction of the model. And here, I want to show is that with purple is the fire weather index, is FWI. And I'm mentioning this because this is an empirical index that most fire brigades in the world are using. It's a Canadian fire weather index. It is very typical, and they are basing their decisions, in Greece is happening the same, based on this index. And it only uses some thresholds on some meteorological, let's say, variables or byproducts of meteorological variables. But this is what is happening in the operational, let's say, field. And all these models that you see that perform better are machine learning models that are considering the local conditions of where we want to predict, or when we move to this yellow line, is a machine learning model that's considering not just what's happening within the grid cell that I want to predict, but is also considering what's happening in the neighborhood, in a 20 by 20 kilometers, let's say, neighborhood, but also what is happening in time. So what were the cumulative effects in time that may play a role in the onset of a wildfire. So this yellow, let's say, line shows that models that take into account, machine learning models that take into account the spatial and the temporal context perform much, much better with respect to what decision makers are using now when it comes to wildfire forecasting. And this is just one example from Greece, and this is from the Mediterranean, how this prediction, red is high wildfire danger, blue is low wildfire danger, can be used in, let's say, predicting wildfires. And this is something that runs now in the Greek Fire Brigade in a kind of a pre-operational, let's say, service, and can be used to allocate effectively firefighting resources. Something that I must mention is that it is nice when we do this and we produce nice papers and we publish, when we have to do this transfer to production environment to what the decision makers need, so there usually there's a big gap. And just to give you an example, these nice models that we're using, and show this very good performance, have been trained using Copernicus ERA 5 data. And this is kind of one of the best available sources when it comes to meteorological data, but in production, these are not available, Copernicus ERA 5. You have to work with, for example, these NWF forecasts. And this is a new noise source that has not been accounted for. So the expected accuracy in production environment will be less than theoretical one. And this is one of the challenges that we address. Now, we do some digging in, what did the models learn for predicting wildfires, some explainability. And we find some nice things like, for example, that wind speed is only important for the day of the prediction, while other variables like temperature or precipitation have a cumulative effect. What has happened in the last 10, 20, 30 days plays a role in predicting the next day, which kind of makes sense. And also, for specific events, we have wildfires and high wildfire danger prediction. We can see that different mechanisms are identified. So, for example, in this scenario here, we have a relative humidity, so increased drought conditions playing a role in predicting wildfire danger. Here it was the wind speed. So this kind of a post-mortem to just enhance our trust in these data-driven machine learning models. And now I stay in the same application, forecasting danger and fire patterns, but now we go from local scale, was prediction 1 by 1 kilometer, to global scale, and prediction on a subseasonal to seasonal scale. So instead of trying to predict what will happen tomorrow in this 1 by 1 kilometer pixel, I'm trying to predict what will happen 2 months from now, 3 months from now in this quarter degree pixel. Right? Different spatiotemporal scales. So what is the motivation behind this? So these are burnt areas for different years in Canada, for Canada. These were extracted from European Forest Fire Information System. And what we want to do first is understand if we are able to capture this interannual variability of burnt areas. But also, if I include here in the figure what happened in 2023, is whether I can predict these extreme years, these extreme seasons of wildfires. So I have these two things that we're trying to do. And the argument here is that when we want to predict so far into the future, we need models that are able to capture these large-scale spatiotemporal interactions that are omnipresent in the Earth system. So Earth is a complex interconnected system, and we have to consider these teleconnections, these long-range spatiotemporal connections in the Earth system in order to model this effectively. And this has been shown to be true for specific use cases. For example, there has been a link between changes in North Atlantic oscillation, which is an atmospheric phenomenon happening in the poles, and wildfires in Siberia. So what is happening is that when we have this phenomenon starting earlier than anticipated, it traps the cold air in the poles. So we have higher temperatures in Siberia. Then the snow starts to melt. The vegetation is exposed to solar radiation. Then we have vegetation becomes drier. And then at the summer, we have extreme wildfires. And so this is a process that has been shown for several use cases. So the idea is to take this as motivation and model this in a data-driven way. And originally, as we're proposing this we found it from European Space Agency project, we argued that we cannot do this with convolutional neural networks because they have a very short inductive biases. They have very short view. So we need things like that. So being able to model, let's say, changes here in the next state of the Earth in another location. So effectively, it's like trying to model the butterfly effect. So something that is, let's say, changing here and now will have an impact in another place in a future time. So this is what we're trying to model. And initially we thought, okay, let's try to use graph neural networks to do that. And we did that, but we have also another nicer result on that. And of course, the first thing that we do, we have to collect all this nice data at the global scale. Again, all these wildfire drivers that we get from Copernicus Era 5, from satellites, and from other geospatial sources. We do some pre-processing to create this Earth system data cube. We have to make some choices about the granularity of the Earth system data cube, so the spatial resolution, the temporal resolution, and so on and so forth. And we'll go to the architecture, at least that we proposed in ICCV, in a workshop in ICCV a couple of years ago, which is called Televit. And the idea here is very simple. So, okay, we have this architecture that is basically using a clever way to tokenize the input, but the clever thing is that we have these three types of inputs. So we have inputs that are local. So the state of the variables and their time series where I want to make the prediction. So NDV, I, temperature, precipitation, all these variables that we saw here. So this is the input at local scale. But I also give the same variables at global scale. And finally, I provide these climatic indices, which I forgot to mention here, that we include these oceanic indices, these teleconnections, as we say, which is kind of the variables that dictate climate dynamics. And if you think about it, what we are giving here as input is the initial conditions at local scale, the initial conditions at global scale, and the dynamics of the system through the climatic indices. And this is what we come up at the end. So this is the different forecasting horizon. Here is the accuracy. And of course, when we want to predict further into the future, so this is like 4 months into the future, accuracy drops. But the idea here is that, first of all, it performs much better than the climatology baseline. But also, when we provide all this information, like the global context and the indices, we get a better performance at longer forecasting horizons. So this is pretty cool. So how do we visualize these predictions? So here we have plotted a sample, different lead times, 8 days, 32 days, and 2 months into the future. This is the ground truth, and this is the prediction. And you can see that at least the changes in the patterns in sub-Saharan Africa are captured really well by the prediction. Also the onset of wildfires in Southeast Asia as well. So there is some predictive skill in this type of models that is interesting to investigate. And when we also do some explainability to that respect, we see that, for example, vegetation index is important when I want to predict, let's say, a lead time 0 weeks, so kind of almost like nowcasting. But for global, let's say, variables, the solar radiation is one of the most important variables, which is what we discussed also before with the Siberia example, that solar radiation is important for vegetation, let's say, humidity and so on. So I move to class imbalance. Let me see how much time do I have. I have 20 minutes? I have 20 minutes, yeah. Okay, so I move to another topic now that is again under the disasters hood, but the main problem that we have is that we don't have enough data to train our models on. So natural hazards are by definition extreme events, are rare events. It's difficult to acquire a dedicated data set for each problem. We have many different landscapes, different sensors, so we cannot have a dedicated data set for each problem and for each setup. And of course, generalization, especially generalization, is always an issue. Here I have a figure from a meteo station in Antarctica, just to highlight the problem. So we have data for more than 30 years of data, and this is the temperature in this weather station in Antarctica. With black lines, you see the different measurements throughout these 30 years plus. With green is the mean, and in March 2022, 18th of March, we saw this increase in the temperature in that station. That, okay, happened within a few days, but still it's an increase that is 40 degrees higher than the mean, than the green. So it's 40 degrees, 40 degrees higher. So this is kind of extreme that it's very hard to predict because we don't have historical data with similar, let's say, patterns. So this is the problem that we're experiencing. And one way to deal with that is to create synthetically these kind of extremes, this kind of data, right? And the good thing is that if we do that, we can create as many as we want and train as big models as we want. But there are problems with that. And the problem is that first we need to find a way to generate synthetically these extremes, these samples. And the way to do that is either use physical models, which is very tough, right? It's difficult to have such a model for all the information that we need, all different types of disasters, different type of sensors, so on and so forth. Or you can use, generative AI to create this sample, and this is something that has some traction in the community, but still it's very a difficult one. But in any case, at the end, we'll have a domain gap. So the real data with the synthetic data will have a distribution shift that we have to find a way to account this for. And I have here an example for an application that is related to volcanic unrest detection using interferometric synthetic aperture radar data. So we have Sentinel-1 data that is a very rich source of SAR data, and INSAIT is a byproduct and can be used for volcanic unrest. It can also be used for landslides that we discussed in the previous presentation. And there are softwares that can create synthetically samples that will have this volcanic unrest as expressed in INSAR samples. But if you use this labeled, let's say, data set, a synthetic data set, and go to the real world, then these models usually fail by a lot. So we have to find these nice ways, like prototype learning, in order to bring the information from an unlabeled, let's say, set of INSAR data, and leverage also the label synthetic INSAR data, and be able at the end to come to this kind of situation where the positive class and the negative class are where are easy to discriminate, right? So the positive class is where we have volcanic unrest, and the negative is when we don't have volcanic unrest. The argument here is that I have to do something to bridge this gap. The next thing that I can do is, of course, take advantage of this very rich source of unlabeled data from Earth observation and do some self-supervised learning so that I learn these meaningful representations, and then starting from this meaningful representation with few labels, I can build my application on top. And there are several ways to do this SSL. We have discussed this throughout the different presentations today. So basically, it's trying to solve a meaningful pretext task. So this is like a game, try to find, let's say, an application, a task to solve in order to train your model using the big, let's say, volume of available Earth observation data. For example, you can take the images, split them into patches, randomize their order, and ask, train a model to find the correct order again. So this is a nice pretext task. We have INSAIT discrimination, which is the contrastive learning that we discuss. SimCLR is one of the traditional ones, and I will discuss this later on. And we have also the mask-to-mask modeling, let's say, to do this self-supervised learning. So when it comes to remote sensing, a nice pretext task, for example, is to predict RGB channels from the other spectral channels. So we don't need any labels. We can create this end-to-end pipeline and solve this problem to learn these representations. There is a downside that you learn an encoder only for the multispectral channel, so it's kind of a limited scope. We have contrastive learning, and again here this is from an application using interferometric synthetic aperture radar data. I did my PhD in SAR, so this is why we like this kind of applications. So the idea here is to create these augmented views of the same sample, try to bring them close in the representation space. If they do not belong they do not come from the same sample, you want to bring them apart in the representation space. The catch is that you have to find very tailored augmentations for your problem and for your data, right? So this is one of the, let's say, constraints that we have. One nice idea is to exploit these natural augmentations that we have in Earth observation. So we get samples from the same location at different satellite passes. So this can be considered as positive pairs for contrastive learning. So exploit the seasonality of Earth observation data to create these natural augmentations. But we can go with a mask image modeling to forget about the need to find nice augmentations. We can do this, and there were some slides about this, using SAT-MAE, where basically we hide some information either in space or in time or in the spectral domain. So there are many different options that we can consider, and then ask this encoder-decoder, let's say, model to retrieve this information, to reconstruct this information at the end. The bottom line is that we are not so much interested in doing this reconstruction really well. It's okay, but this is not the objective. The objective is to find a nice encoder that then can be used for the different downstream tasks, all right? And one thing that I would like to mention for all these different SSL approaches is this difference between fine-tuning a model and linear probing. So it's a different thing of having a new application where you append a linear layer and train only this linear layer, and a different thing when you want to unfreeze this encoder and try to fine-tune it from scratch. So it's a different kind of objective. And I move to the foundation models in Earth observation. So the idea here is to create this logical next step from SSL, these foundation models that are able to capture the information in a meaningful way from Earth observation data, accounting for the different scales of the objects that are on the Earth, the different sensor modalities, the different ground sampling distances, so resolution, and the different environmental conditions. So create basically a generalist model that can capture all this information so that I can solve these different downstream tasks. And this is, I think, from Alex's work, this nice figure here. So the idea is to do the cell supervision here and the fine-tuning to solve the different tasks here. In order to do that, we need data sets, and we have several pre-training data sets to do that. Here is some examples that people usually exploit in order to create these foundation models. I would just like to refer to this nice Copernicus foundation model that will be presented next month in ICCV. It was a work that was led by Yi Wang from Technical University of Munich, where basically we have, let's say, aligned many different Copernicus Sentinel modalities, Sentinel-1, Sentinel-2, Sentinel-3, and Sentinel-5P as well. Let me see, yeah. Sentinel-5P as well, including Copernicus digital elevation models. And we have done this in a granularity that is quarter degrees, so that we can, in the future, integrate in an easy way Copernicus Era 5 data that come at the same resolution, quarter degree, as well. So, and then we have all these pre-training data sets, and we train these foundation models. And we heard a lot about foundation models. Here I have some examples in this table here, and with the different learning strategies, or contrastive, or mass-to-mass modeling. And we have big and with lots of parameters, less parameters. But I like this figure here that you cannot actually see. This was presented last week by the defense thesis of Yi Wang, and I got some license to use it. These are the different foundation models in our community, in the Earth observation community, starting from 2021 to 2025. And this, okay, on the one hand, this is very nice because it shows that a lot of people are working on this topic. At the other moment, it provides a hint that we're not in a kind of a ChatGPT, Gemini, Claude kind of moment here, because we have many foundation models, and many are coming also in the near future. So this is something that I would like to hint, I would like to discuss as well. In order to assess these foundation models, we need benchmarks, and we have benchmark tailored for Earth observation data, where we have different modalities and different tasks, segmentation, object detection, classification, and so on and so forth, and benchmarks for weather data or for climate data. Well, at the end, we want to be able to generalize across the diversity of the Earth, be robust to real-world challenges, produce quality representations, which are quite vague, but it is important, and be broadly applicable to different tasks. So a very brief history of foundation models in Earth observation. We started with Prithvi, that was basically trained on Landsat and Sentinel-2 multispectral harmonized data. So it was kind of a single modality foundation model. And we say, okay, foundation models should be more than that. So we go to multimodal Earth observation models, and we heard today about Smarties or EarthMind, for example, that go along this direction. I have here DOFA, which is one of the works we did with TUM, designed to adaptively alter its weights in response to new data modalities. We have FOMONET from my PhD student Nikos Boudos that trying to do something similar, and we have also Copernicus Foundation model that was pre-trained on the Copernicus, let's say, benchmark that I showed you before. They are all doing some really clever things in order to be able to adapt and leverage all these different modalities, which is nice. But the one of the, let's say, criticism is that, okay, Earth observation data is by definition multitemporal, and we do not consider this with these foundation models. So there are works in this direction. So we have Presto, and now we have Galileo that explicitly try to model this multi-temporal pixel level, on the pixel level aspect of Earth observation data. But again, the criticism is that, okay, these are works, research works, we need to scale everything as ChatGPT has scaled in this massive, let's say, using massive resources. We need to scale everything, and we have things like Terabyte by IBM that is trained on a massive data set, really, and has this any-to-any generational capability. So we can even input some modalities and get in the output here another modality. So you can input Sentinel-1 and request as an output Sentinel-2. You can do the typical things that you do. You append a task encoder for a specific downstream application and fine-tune, or you have this thinking in modalities concept, so you have a specific problem to solve, and if the model understands that it needs an additional modality that was not input in the first place, it generates this modality and uses this for the downstream task. So this is pretty cool. So it looks like problem solved, but I came across this nice, let's say, blog post that's called Geospatial Foundational Models, Geospatial Foundational Disappointments, that is basically arguing that we are using all this massive amount of data and processing, and what we get at the end is we get a marginal improvement with respect to a supervised unit, let's say, baseline, specifically for TerraMind, and for the Pangea benchmark that I showed before, it's also losing in 5 of 9 tasks. So we get all this effort, all this data, all this pre-training effort, but we get really something that is marginal. So again, this is a hint that this is not a ChatGPT moment for Earth observation foundational models. We're still missing something. And with that, I would like to also to mention some limitations. So my outlook on the field. So the truth is that there are many shortcuts to achieve higher performance in this benchmark, but we really need some ways to model how these foundation models encode these intra and intermodality properties and relationships. And many times it's difficult to assess in an objective way whether we get this performance boost due to the pre-training, data pre-training, due to the model architecture, due to the benchmark that fits this model better. So we have to conclude. Yeah. Okay. So for me, this is something that we need to do in a methodological way to evaluate the extracted representation, since it's something that needs to be done. We also discussed this, I think it was Davis Tuia that mentioned in the presentation today, that do we really need all this data to do the pre-training? And there is some rationale in that we do not need all this data. Earth observation data are inherently very redundant, so we should find clever ways to address this. And also, when we go and fine-tune the entire encoder that we have pre-trained, this is really not, that defeats the purpose of the foundation model. We should not unfreeze and, let's say, fine-tune the entire model. This is really not a foundation model. So, and other things that we need to consider. And I would like to close because I don't have, with this, some outlook. It's nice that we discussed about pre-training data sets, benchmarks, models, foundation models. We saw this tree of foundation model. Now we see in the last few months, even more than that people are trying to forget about the models, forget about the input data. Let's go directly to the embedding space. And we produce embeddings. And one of the first efforts was done by Klemmer et al. That used CLIP to train this location encoder. So what they're basically saying is that give me your location and I will give you the embedding. And they did this using Sentinel-2 data, and I found some locations that are very, let's say, close to each other but different. They are far to each other but similar, so there are some very nice properties. we did something similar with the Copernicus Foundation model that we presented in ICCV. And this is just a PCA of a very big vector. I think it was like 700, let's say, dimension or more. And we have, of course, the Alpha Earth by Google DeepMind that has released these global embeddings. And it is very nice because they're providing embeddings, one embedding, let's say, of dimensions 64, every 10 by 10 meters, so very, very good spatial resolution, excellent spatial resolution, and they provide this once per year. So from 2017 up to 2024, we get a different embedding for every 10 meters on a global scale. So nice ideas, for example, is whether we can use these embeddings to forecast the embeddings of 2025 or 2026, because now we have also time series of global embeddings. So these are nice things. I have another section which is about uncertainty, but I think we are off time. So with that, I would like it's better to conclude. Yes? Thank you very much for your attention. Right. Yeah. Just to mention very briefly, if you want to visit and see the research that our lab does, and also we are going to have a spring school in AI for modeling and understanding climate extremes on March 2026. This will happen in Athens, Greece. It will be co-organized with ELLIS unit Jena in Germany, and we welcome everybody to come to this summer school. Any questions?
Thank you very much for a very interesting talk. Yeah, with that, we are open to questions. Please go ahead.
Thanks from me as well for the interesting insights. My question is about your work on wildfires, and actually mostly about your experience. It's a problem where on a high level the relevance is almost obvious, but in my experience when you start to dig into the use cases it gets a bit trickier. Because, for example, the use case that, in my experience, is most often thrown around in requested is parcel level risk. Like was said earlier, you obviously don't want to build a house that's likely to catch wildfire. But when the risk forecasting is lower resolution, like in your work, say kilometer by kilometer, it's no longer as relevant for parcels because a lot of the fine-grained details are lost. So I wonder, in your experience, what's the best use case for these like low resolution risk rasters, and who would they most help?
Okay, so if I go to these bridges, okay, it was in the beginning, yeah. So just to clarify, and maybe this was my mistake, I mean, we are trying to forecast danger, hazard, not risk, because when we discuss about risk, then we bring the assets into the equation. So the population, the natura areas, industries, and their vulnerability. So we're trying to forecast hazard. And this can be kind of more objective with respect to the physical phenomenon. So the accumulation of heat, lower precipitation, lower relative humidity, close to populated areas, an old forest, so low NDVI, all these combined lead to an increased danger. The impact is when we consider what is the vulnerability of the asset, of the population, of the houses that you mentioned. Now, in practice, I don't have this map, but if you see what the Greek Fire Brigade is using in order to make day-to-day decisions on where to allocate the resources, moving firefighting planes, moving firefighters, in preparing for the next day, they're using something that is kind of on a perfection level, wildfire risk assessment, wildfire danger assessment, using fire weather index, an empirical index, on a much coarser scale. And based on that, they're doing very costly things, like moving people around. Yeah, so 1 kilometer by 1 kilometer, I think it is good enough for allocating resources. Going into more high resolution, it will be tougher. I mean, if you have something in 10 meters, you cannot have a firefighter every in every pixel.
Yes, thank you. And do you think, apart from governments, do you think there could be some other use case for these lower resolution hazard rasters?
It's not just government. It's everybody that is needs to take some actions based on wildfire danger. Another thing is, for example, bigger industrial players like power, let's say, transmission operators that are generating electricity. They have these business continuity departments, which basically say what will happen, how will I continue operations, because my operations are critical for my business and for the world. If I have there is an earthquake, if there is a wildfire and I lose this power plant. And so there are also others that can be, that can use this kind of information as well.
Yeah, I understand. Thank you very much.
Are there other questions? I'll ask one question in the meantime when others are thinking. Okay, actually 2 questions. Especially about this 2023 that you show the fire events, and that's quite high compared to the other years.
In Canada, yeah.
Yes. What is the particular reason behind this? More importantly, is that the recurring phenomena that happens like throughout the history, or that is the particular year?
This was a particular year in Canada, so these are actual data, it's not forecasts, it's the burnt area, so what actually happened.
Yeah.
And it was an extreme year. So I don't know the underlying reasons, so I have not read at least what were the environmental conditions that led to such large wildfires in Canada. But we see this happening in other places in Australia as well. So we have some extreme years in California. In Greece happens the same. So in Greece we had in 2023, again the same year, the largest ever recorded fire in Europe, right? And there are several reasons. Some of them we cannot even understand because they can be, as a consequence of climate change, but not, something like, an increased temperature, but very small changes happening in mean temperature or mean relative humidity. Small changes, but combined they can create these tipping points that can have a very big impact.
These are sporadic, or they are rather periodic? It may happen.
It's
like
sporadic.
Sporadic.
You cannot see wildfires, especially in Africa, are very periodic. So there is a seasonal effect, but extremes are not periodic. Yeah.
Okay. So the other examples that you showed about this 40 degrees high in temperature, that look like more of the sensor failure or actually happens. So is it? Is it also reported by the people, or also only by the sensor in that particular example?
No, it was not. It was
indeed recorded.
It was indeed recorded. Yeah, yeah. It was recorded, and there was a big fuss about it. Yeah, because imagine going out and it's 40 degrees higher than you expect. Yeah.
And the reasons to this is not known, or?
I must admit I don't know. Maybe they are known, the underlying phenomena that led to this extreme. I just saw this observation. I thought it was really just to make the point that it's difficult to model this with machine learning and anticipate this with machine learning.
Okay. All right. Thank you. Are there questions? Okay.
Hi, very nice presentation. Yeah, so in your slide I show you are using graph neural networks. So is it possible to use physics-informed neural networks like neural operators, like graph neural operators, to use both physics and neural network together for forecasting? And one more thing, like in this slide you're showing that class imbalance. So how are you using, like which loss function are you using in your architecture for tackling this class imbalance? Are you using some kind of dice loss or focal loss or something like that?
For which one?
Class imbalance.
For this one?
Yeah.
Well, I mean, it depends on the application, whether we are, doing segmentation or classification. So it has to be. It's not a a one solution fits all, right? It has to be specific to the problem. For your first question, which was about
physics-informed neural networks.
so we have not tried this. In principle, yes. What we have tried is to use all this information to create what we call causal graphs. So do causality to create this causal graph. So have these, let's say, links, causal links between the variables and the outcome and the time lags, in order to create, in an educated way, this graph neural network and then train it. So we have this graph neural network, but we created this using some, let's say, domain knowledge coming from the causal graph,
okay.
but
so
not using GCN.
But in graph neural network, the data will be like very high. So like for training it, it requires a lot of computational resource. So is it possible to train the data in lower resolution and test it in higher resolution? Is it possible, something like that?
Yes, we can do that, and we have made, some experiments. We have resampled this cube, for example, into 1 degree resolution. We are also done some work using GraphCast. You know GraphCast?
Yes,
yeah?
yes.
So this basically uses many different kind of resolutions, pyramid of resolutions, and try to do some training on more coarser, let's say, resolutions, and then try to fine-tune it on specific locations at higher resolution. So not globally, but in California and in Greece and in Australia, for example, in more fine-grained information.
But GraphCast, they have said that they have not incorporated periodicity. So that's why they bring forward GenCast, where they're using diffusion models to...
We have not tried that, but this is
okay.
a nice idea.
Thanks.
Yeah. Thank you.
All right. Any further questions? Okay. If there are no more questions, then let's thank the speaker again. Let's thank him.
Thank you.
So, quick announcement for tomorrow. There is a slight adjustment on the schedule. You can check it online. There will be a poster session instead of one talk that was pre-scheduled. That was supposed to be remote, but that is not possible. Therefore, there will be poster session that will be the second talk of tomorrow. Other than that, the schedule remains the same. With that, we end up today's session here. Thank you very much for joining, and see you tomorrow at 9 o'clock again. Bye-bye.